Hello everybody, we are back with this fluorescence spectroscopy. So, in our last lecture we talked about the ingredients of the important ingredient of this ultra fast studies, and in that case the most important ingredient is the light source. Okay. Because if you do not have the light source, then you will not be able to study this. Now another important point is with respect to ingredient is your this chemical system, I mean the system which you are going to study, that is another important thing, because you would apply this fluorescence techniques or time resolved fluorescence techniques to to study the various events. Okay, various events means time sliced to study events at different time scales. Okay, so chemical system or these the molecules of interest, that is very important. Okay. But apart from that, whenever you talk about this ultra fast or fast studies, so you have got a detector. Okay. So detector has got some inherent slowness or fastness. Okay. Suppose you use this short pulse from lasers, I mean from appropriate laser, I mean appropriate frequency short pulse lasers. Okay. Now the point is that although you can initiate the process, I mean your process which is occurring. Okay. So that is maybe slower compared to your light pulse width. But suppose your detector is very slow, then although the process has taken place quite fast, but your detector could not do it. So basically this if it is not fast enough, or if it is not able to transfer or transmit these events in a very basically very fast, I mean the thing is that suppose it is accepting some information or getting some information, and after getting it should immediately transmit that information to the computer. So if it is not able to do that, that means if it is limited, its efficiency or its fastness is limited, okay, compared to the fastness of the process of your interest or your system, then it will not happen. I mean you won't even be able to look into your desired events. So what you need to get appropriate detectors. Okay, like detector should be fast enough. Okay, but again electronics, I mean the fastness of electronics is limited up to certain level. Okay. So beyond that what you are going to do, I mean beyond that what you are going to do means I mean suppose the fastness of your detector, although your detector is fast, but suppose this electronics, okay, electronics which is going to digitize the information, okay, which is going to digitize the information one after another. I mean, so the detector is sending its signal to the maybe to the digitizer or to the electronics part of the system, to the card, I mean which contains the electronic part. Okay, electronics part. So what is happening that this electronics part should be able to process the train of informations that is being transmitted from your detector to this. So suppose if it is transmitting information at a much faster rate compared to its processing ability, then some of the informations, what will happen in between informations may not be processed by this. So, you may lose information, So, in that case, something else, you need to think of something else. Okay, that is your detector. It should not be detector dependent. So you need to, time slice in a different fashion. Okay, taking into consideration that approximately in 1 nanosecond, light, it travels about 1 foot. So using that, mechanically maybe you can do this time slicing. Okay, mechanically you can do this time slicing. So that thing that particular thing I am going to talk about maybe a little later. So right now, we talked about this, already talked about this one, and we are now in this region, basically faster time region, in this region, okay, like 10 to the power, say minus 11 to say 10 to the power minus 15 in this region. So it is really fast time scale. Okay, so we are interested to look into these events. Okay, so resolution thing I already talked about. So now how to, but the thing is that you need to generate this pulses, pulsed light, pulsed lasing. So how to generate pulses? So typically one is called Q switching. Okay, another is called mode locking, and remaining are the pulse shaping, pulse shortening or pulse lengthening. Okay, these are the things that one should consider while dealing with this pulses. Okay, so lasers are for pulse lasers. Whenever you talk about lasers, these are the most familiar terms, especially for fast lasers. Now, what is Q switching? It is presence of oscillating beam inside the cavity, and what will happen, basically alternate presence of oscillating laser beam inside the cavity. So the moment, when you think about, say this is your mirror, these two end mirrors, okay, and one is output coupler OC, that is about 99.9% reflecting, it is 100% reflecting. So point is, these mirrors are very special mirror. You see that it is 100% reflecting. It is not that for the entire range of frequencies, range of wavelength. It is 100% for a specific range of, specific wavelength. The corresponding wavelength corresponding to the lasing frequency. And so you have got this active medium, this laser rod or the lasing active medium or the molecule. Okay, this is 100%, 99.9%. In order to get pulses, what you do? The thing is, then put a card, say visiting card, maybe in between this and that, just put a card. What will happen? This laser oscillation is stopped. Okay, then at some moment of time you take out this. What will happen? Again it is lasing. So if you can do like this, or maybe if you now rotate this mirror, Rotate this mirror means you have this mirror, you have another mirror, okay, you rotate. So, when it is exactly, I mean these two mirrors are exactly parallel to each other and vertical to the standing wave pattern that is generated, then and then and only then lasing is there, I mean oscillating laser beam is there inside only. Now, if you rotate a little bit, then what will happen? This reflected beam from this particular mirror will not remain inside the cavity. So, it will ultimately after 2-3 multiple reflections, it will leave the cavity. So, that means oscillation, laser oscillation or lasing will be stopped. So, if you keep on rotating, no lasing this way, then ultimately again when it is exactly parallel, then again it is lasing. So, although this is a mechanical process, so it takes time for the mirror to rotate so fast. So, that means you will get on off kind of this this not like this exactly, maybe depending on how much time this, maybe this is very short, how much time this mirror is exactly parallel maybe depending on its speed. Okay. If it is very slow speed, then this will be maybe little wider. If it is very spinning faster, then it will be shorter like this. Okay. So, on off, okay, then on off like this. So, for this time it is on. So, you will be seeing some light is coming out, then off, then on, then off. This way it will continue. Okay. So, that means you are able to get the pulsed light. Pulsed light means on off. So, basically it will be like the moment it is exactly parallel, you will get a flash, I mean laser flash. I mean flash means you will get lasing light. Okay. Then it is little, if it is little tilted, no lasing, again tilted in the other in the reverse direction, lasing, no lasing, no lasing. So, you can vibrate it as well like this, not only rotating, but you can vibrate, lasing on off it will do like that. Okay. So, this is one thing, and if you think of this cavity loss, so with time you see that for some time this I mean this is your cavity loss is 100%, this then cavity is gain. So, cavity gain is this way. So, here this is your output intensity. Okay. So, whenever you do this type of mechanical process, there may be another technique which is called the saturable absorber. Generally dyes are used. So, that is also doing the similar kind of thing. Okay. Then another thing is optic shutter, that is called the Pocal cell. Pocal cell or Kerr cell, it is basically an electro-optic arrangement where this Pocal cell is allowing, I mean you can put one Pocal cell over here, and this when you apply electric field in the Pocal cell, it changes its polarization state. So, when polarization state is changed, so it is no longer remaining in the same polarization state. I mean this reflected one, when this reflected back reflected one passes through the Pocal cell, its polarization is getting changed. So it is no longer oscillating. So, when Pocal cell is off, then it is oscillating, or when the Pocal cell is on, it is not oscillating. I mean this way, I mean depending on the polarization state, you can get an on off kind of thing. Okay. And generally this type of process, I mean this Q switching is generally used for I mean nanosecond time scale, nanosecond lasers. Okay. Then is another called is mode locking. This is commonly observed in case of this short pulse ultra short lasers. So, there is a shutter between mirror and gain medium. Okay. So, and shutter opens, all mode gains means all modes gain at the same time. So, basically you see that random, when the phases are random, okay, you see it is random. So, here if you think of, here also it is out of phase, you see this is down, this is up, this is down, this is up, this is down. Okay. So, that means they are not constructively interfering with each other in all the cases. Okay. Okay, constructively. So, basically what is happening, that all the means in course of time all the modes are all the modes are out of phase. Okay, these are individual modes we are talking about. So, mode locked phases means, in case of mode locked phases for lasers, when all the modes are locked at a specific time, means at some interval all the modes are locked. Okay, then after another interval you will be getting a mode locked. So, it is not always mode is locked. So, what is happening, that at this particular time all the modes are in phase, but here it is not in phase, this is also not in phase. Okay. So, you are getting, so when the phases are locked, then basically you will be getting ultra short pulses. So, in all other region nothing, you are not getting anything. So, intensity is 0, then again after some time you will be getting another like high intensity, but here you see that phases are random. It is just like light bulb you are generally you can generally think of. Okay. Basically when the shutter opens, all modes gain at the same time. Okay. So, basically this way mode locking is basically the principle that all the phases are phases are such, or they are relative, this time is so chosen or so chosen that all the modes are constructively interacting or interfering. Okay. So, that is called mode locking. So, active mode locking. So, mechanical shutters you can use, it is called the acousto or optoacoustic switches, like similar, which is called called a focal cell. Okay. So, acousto-optic or optoacoustic modulator, and synchronous pumping can also be possible. Passive mode locking by means of colliding pulses, or maybe by means of another called, which is Carl lens mode locking, which is basically a lensing effect is happening when your active medium is solid. Then because of this, because solid means it has got some lensing effect. So, in that case, due to this lensing effect, this mode is locked, which is called this passive mode locking. So, mode locking is a very important thing, that is mechanically you can mode lock by putting a shutter and then opening the shutter at a moment when all the modes are in phase. Okay. So, that you can do, or maybe by means of passive way, that is called, one of the important commonly used one is your Carl lens mode locking, KLM. Okay. So, Q switching and mode locking, these are very important important factor. Okay. These are mode locking methods. Now, next is called pulse lengthening and pulse shortening. Okay. Pulse compression and pulse stretching. Now, what is exactly happening now? So, if you have a short pulse of light, what do you expect? That you have got any medium. Okay. So, what is exactly happening, that this pulse means it is basically, you know, if it is a short pulse, that means its bandwidth is more as per this time frequency uncertainty. So, this is your frequency spectrum, it will be broader. Okay. Broader means it will have more frequencies in that pulse. In that case, single frequency or monochromatic lasing, it's a gross term and should be used with caution, because when it is a short pulse lasing, then you can expect to have this many frequencies to be there, to be present there in a pulse. So, this many frequencies are there. So, the more compressed thing, the more compressed pulse, the more is the number of frequencies that are present out there. Now, if you allow this frequency to pass through some medium, okay. So, basically what is happening, if you allow this short pulse to propagate through any medium, then what is happening is called the group velocity dispersion, GVD. Okay. So, since it is composed of this many frequencies, you see, so maybe this side is higher frequency. So, this is blue, this is red. Red means it is not in true sense blue red, this is the higher frequency side, this is the lower frequency, bluer side, redder side. So, what is happening, that when this pulse is passing through, okay, is passing through this any medium, then this different frequency which are initially moving at, okay, moving at the same velocity in maybe in vacuum. Okay. Now, when it passes through any medium, then these frequencies, these different frequencies are moving at, propagating within this medium, in this active medium, or maybe some not active medium, but any medium within a medium. So, different frequency of light is they are moving at different velocities. So, that means, so suppose you have got nu 1 and nu 2. Okay. Initially these nu 1 and nu 2, they are moving like this together, okay, in this way. Okay. But after it is passing through this medium, okay, suppose this is nu 1 and this is nu 2, what you get, that they are temporally separated. Temporally separated means, when you look at here, maybe if you have some detector such that it is able to see it, then what is happening, that maybe you see that nu 1 is coming at a later time compared to this nu 2. Okay. So, what is happening exactly, that your initially your pulse width was like this much, say this much is say 2 femtosecond. Now, this pulse is after coming, so you see that you have to count up to this. So, it is stretched, because of this group velocity dispersion, this pulse became stretched, a little stretched, and this is called this chirping of pulse, it is called the chirped pulse, and it looks like this. Okay. You see that it is broken in many into this like this. Okay. So this is something, whenever this is something that is happening, like whenever you why this is very important, that suppose you start with a 2 femtosecond pulse, or maybe say 10 femtosecond pulse, and you are allowing that pulse to pass through many different optical components like mirror, maybe mirror, maybe prism, maybe lens. Okay. So, in these different components, because they are made up of different glass like material. So, when it passes through or when it is reflected back by those things, those parts, then this type of lengthening of pulse is possible and is said to be, the pulse is said to be chirped. Okay. Now, how to do this pulse compression? Now, in that case you need to have this this type of arrangement, that is this 4 prism design, that you have got this chirped pulse. Okay. This side is red, this side is blue or maybe yellow, little bit, I mean little bit of it is not that all red to blue is there, maybe a fraction, I mean a portion of this spectrum is there. So, although it is much broad, because I mean since it is chirped, it has become broader. So, you see that it is, this is red, this is blue side. So, in reverse prism configuration you see that this is now passing this medium for longer length than this yellow one, although yellow is a little bit delayed. Okay. Then yellow is passed through, yellow side is passed through, again you see that here it is passing less, it is passing less. Okay. It is passing less, I am passing through this mirror, I mean this your prism material less, but this red is still passing more, I mean more length through this mirror, I mean through this prism. So, what is happening, that this red has to travel more glassy material, glassy substance than this one. So, whatever chirping that has occurred due to passage through this medium now has been compensated due to complementary this passage, that is less through this glassy material for the yellow light and more through this glassy material for the red light. And in effect what is happening, that they are now this is the one which was initially delayed, is allowed to get delayed less than the one which is not delayed initially. So, what will happen, that now this is moving a little faster, and after passage maybe they are coming close. So, therefore, the pulse is now getting getting compressed. So, this is one method of pulse compression. So, you see that why I am talking about all these, because of the fact that to give you just an overview of what is there in this ultra fast systems, and how this I mean means why this is really required. I mean, in case of nanosecond processes, when you start with when we talk about this nanosecond optical, I mean this phenomena, then these are not important. Okay, because you see in 1 nanosecond light can travel about 1 foot. So, it is much larger, but when it is when it is a very short pulse, then it is composed of many frequencies. In case of nanosecond, it is, since its energy uncertainty, I mean time uncertainty is less, then energy uncertainty, I mean time uncertainty less means energy is more, I mean it is broadening is less, because delta t delta t and delta nu. So, delta t, I mean if it is, I mean delta t is more basically, because nanosecond energy uncertainty is more, because it is a long pulse. So, therefore, its frequency uncertainty will be less. That means, it will not have those many frequencies. It is not expected to have those many frequencies, but for the short pulses like this picosecond, or I mean like the femtosecond pulses, these are very important. Okay. So, in those cases, these modifications and this compensation, I mean compression, pulse compression, when a pulse is chirped. Okay. So, this has to be done in order to correct this group velocity dispersion problem. Okay. So, just getting a laser light, I mean very short pulse will not solve your problem. Okay. Why will not solve your problem? Because of these many complications are there. Okay. So I guess I could give you the idea of pulse lengthening and pulse compression, pulse shortening, I mean pulse chirping and pulse compression. Okay. So short pulse amplification, I mean you have short pulse, then dispersive delay, okay, giving rise to this dispersive delay means it is now dispersed. So short pulse is now dispersed. Okay. So I mean delay in the sense that you have got a dispersive medium, okay, such that these individual frequencies are now given one after another with a specific time difference. That is, they are not allowed to come at the same time, but one after another they are coming. So that is dispersive delay. Then you have solid state amplifier. I mean amplifier means maybe amplifier is basically amplifying amplifying your pulse, and then so it is a basically you see that it is a wide pulse with sufficient number of photons, I mean sufficient number of photons over here. You see that area over here was very small. Now this area over here is much high. So initially maybe you can think of, say for example 100 photons, now it has become maybe 1000 photons, okay, or maybe 50,000 photons. Okay. So what is happening, 100 to 50,000, okay, it is a huge increment of number of photons. Okay. Initially it is 100, so 50,000 to 100, that means it is about 500 times increment. Okay. Now what you can do, if you now can compress it by means of a pulse compressor, so then it will be a short pulse and its intensity will be huge compared to your this short pulse which you got from the oscillator. So basically you can use a short pulse oscillator, then you use some amplifier, solid state amplifier, and then pulse compressor. Using the pulse compressor you can recompress it. Okay. So this way you can use this chirped pulse amplification, pulse chirping, then amplification, then pulse compression. This way you can generate huge intensity short pulses. Now palm probe technique, I mean as I told you in this ultra fast spectroscopic studies, this palm probe technique and fluorescence upconversion technique, these are the two complementary, in some cases these are the two important techniques that one can basically one can study various chemical processes. Now what is happening over here, you have this laser light which is the very short pulse, and basically it is the absorption technique. Okay. It is not an emission technique, but just for relevance I am giving you the information that you have this okay, this is your this is your basically this is basically your single color. Okay. It is not a two color, it is single color color study. Basically what is happening, that you have your laser, then you have a this pulse divider, I mean this it is your 50-50 beam splitter. So that it is divided into two parts, maybe it is 50-50, or in some cases it may be 10% and 90%. Okay. So probe light is generally weak, and pump light, excitation light, should be intense. So you see that it is divided, it is into two. So some percent with the help of a delay line, it is your probe light, and then it is passed through your sample, and major portion, it is with the help of a delay line, it is passed through your sample. So this is your excitation pulse. After excitation, the excited ensemble of molecules are generated. Then your probe pulse is generally used. Probe pulse is generally used to detect it, and maybe in some cases your probe pulse, from your this red probe pulse, you can generate white light. That white light can be used to detect, I mean used for probing the various species. So basically change in probe pulse intensity, probe pulse intensity as a function of delay. Delay means basically it is you excite at a particular time interval, and then with respect to that excitation pulse you are time slicing. I mean this is your excitation time position, and this is your zero line for your probe light. Okay. Now you scan it at different time gap with respect to your this excitation pulse or pump pulse. So that will give you the idea that after this excitation how much of excited ensemble is there, okay, with the help of probe light, because if excited ensemble is more, then your more of probe light will be absorbed. That is, you are just doing the absorption like you are in your absorbance spectrophotometer. So only thing is that in absorbance spectrophotometer you are probing the ground state, but here what you do, you use this excitation or maybe this pump pulse to pump your system to this excited state, and you monitor this excited system, I mean this excited as a function of time, okay, as a function of time. And of course there is a possibility of ground state absorption, but that can be eliminated by simple subtraction. Okay. So that will give you the change in, I mean delay versus change in probe energy, probe pulse energy will give you the idea of how much of absorption is there. So your zero time is fixed by means of just measuring this length. I mean from here the pulse has been divided. So this much of length should be equal to this length up to this at zero time, okay, at zero time. So basically this way you can this is an absorption technique. So you can follow the excited ensemble of systems in ultra fast or in faster time scale. Okay. Now next is another technique which is very important. I mean since I told you that this probe pulse can be made, I mean made to be to be white light, like with the help of some sapphire disc. You can put a sapphire disc over here so that this probe light becomes, I mean sapphire disc over here, so that this probe light becomes white light. Then you can scan as a function of different frequencies as well. Okay, you can probe with the help of white light. So anyway, so in that case you need to have a monochromator, otherwise you won't be able to see which frequency is particularly absorbed to what extent. Okay, so this is you can generate white light, means like you can, if you have a ultra short light pulse, then since its instantaneous energy is very high, it's because its pulse width is small. So peak height is very high, and as I told you that this nonlinear process, because intensity high means a nonlinear, various nonlinear processes are going to happen. So, when this particular this high intensity pulses, I mean high intensity ultra short pulses or light is focused on, like the sapphire disk or maybe quartz or ethylene glycol, then when it is focused, then intensity at this point, means at the focusing point, will be very high, and therefore nonlinear processes will take place and white light will be generated, and this white light, with the help of a prism or maybe with the help of a monochromator, you can generate this ultra short, this white light. Ultra short white light means different frequencies. Okay. So, this white light is sometimes very useful in this context. So, different experiment, transient absorption, as I told you, that the typical setup which I have, I mean this typical schematic what I showed over here, this is palm probe transient absorption studies, and there is another technique which is called the fluorescence upconversion. Okay. So, fluorescence upconversion means it is the amalgamation of photons. Okay. So, amalgamation of photons. So, it is basically you have your suppose you have one photon, you have another photon. So, you can amalgamate these two photon in some medium. Okay. So, these are called like in some crystals. Okay. So, like beta barium, beryllium borate, or this type of crystals, when you shine your this two pulses like omega 1 and omega 2, then you will get a frequency, some frequency of omega 1 plus omega 2. So, in a nonlinear crystal, some frequency is generated. So, omega sum is equal to omega 1 plus omega fluorescence. This is the second photon. Okay. It is generated. So, it is energy conservation and by phase matched interaction. Phase matched interaction is a particular thing. For phase match interaction means it is a momentum conservation. Okay. So, phase matching is required. Now, basically what is happening, that you have this laser pulse, this omega 1, then nonlinear crystal, then omega 1, omega 2, it is generated. Then with the help of optical, I mean you have this this in nonlinear crystal. Okay, you can generate basically you can generate two frequencies. Okay, in some nonlinear crystal. Okay, then from omega 1 you have omega 1 and say omega 2 by means of say some nonlinear in some nonlinear fashion. So, what is happening, that maybe it is a maybe some frequency omega 1 plus omega 2 that can also omega 1 plus omega 1, that is 2 omega 1, that may be there. So, you have this omega 1 with the help of a dichroic mirror, you can separate them. So, omega 1 is omega 1 is here with the help of this optical delay line. It is okay, with the help of optical delay line, it is going this way. This is omega 1, and this omega 2 with the help of another optical delay line, you have a sample, then half wave plate. Then half wave plate means this half wave length changing. I mean, okay. So, it is called the half wave wavelength half wave plate. Okay. So, then it is focused, I mean it is allowed to fall on over here, and then both of them are allowed to fall over here. Okay. With properly orienting this half wave plate, you can match this. Basically you have to match the phase. Okay. So, that is why phase matching is done by the help of this half wave plate. Okay. So, it is this wavelength by 2, this much of, or it in some cases quarter wave plate are also there. So, but here half wave plate is used. So, using this half wave plate, then this your fluorescence, then after half wave plate it is allowed to fall on your nonlinear crystal, and then ultimately your omega 1 plus omega FL, that is omega sum, is generated, and with the help of a monochromator you can identify it. Okay, you can detect it. Okay, so this is another diagram. 100 femtosecond, 800 nanometer. This is your this is pulse. This is your gate pulse delay, your sample, and this is your this is your sample. So second harmonic crystal, with the help of second harmonic crystal you are generating blue. With the blue you are exciting it. Then you have this your this lens which is focusing on your this upconversion crystal, and then here this is phase matched in a proper fashion, so that this upconverted beam is coming out in a particular direction, and then it is a spectrometer, and with the help of the spectrometer you have detector to your computer. So it is this way you are getting your upconversion signal. Okay, so this is a typical where it is this nonlinear crystal is your second harmonic generation. So the second harmonic crystal, blue and red, then blue is directed this way, red is directed here, and then these two are with the help of proper phase matching. With the help of proper phase matching, you can do this this phase, and of course this polarization. Okay, so basically this is half wave plate is half wave rotation that can be this much of polarization change it can do. So basically same thing in a it is described in a different fashion. Okay, so then this is another modern spectrometer. You have got this elliptical reflector, this is your sample, so that it can collect the whole emission using this elliptical reflector. Then it is your upconversion crystal, and then these are your this is your red, this is your yellow, this emission, and this is your what is called upconverted, that is some frequency over here, then prism to your monochromator, and ultimately to PMT. Okay, so this is the typical apparatus. An advantage is high time resolution, limited mainly by laser pulse duration. So if laser pulse is very short, then your time resolution will be better. Disadvantage is limited sensitivity, decreasing with increasing time resolution, and also crystal thickness is a factor. Okay. So sensitivity and also this crystal thickness is a very important factor for your resolution. Okay. So some example that this DMABN, this is a classic example that this is your absorption, this is locally excited in N-hexane, and this local excitation in it is ICT. In acetonitrile it is locally excited is very less, and ICT is major. So large red-shifted fluorescence intramolecular charge transfer ICT. So basically we already have talked about, but using this fluorescence upconversion technique, you should be able to also see this. This is one example basically I am giving you. So this is the typical two-state model, and these are the temporal profiles that LE and ICT. So this is for ICT state, and this is for local excited. You see that local excited is decaying, and ICT state is growing, and then there is a rise. Okay, and then it is decaying. So, and this is your TCSPC where excited at 267, system response is greater than 30 picosecond. So you see that LE and ICT these are monitored around this region. So different profiles, upconversion profiles in acetonitrile. You see that 325 in the bluer side, you see that there is the decay, and you see in the red side 550 and 575 it is growth. So this way you can using this fluorescence upconversion technique, you should be able to monitor, you should be able to monitor this fast process. You see that it is 20 picosecond, okay, very fast processes you can see. So, anyway, so using this fluorescence upconversion, although I could not give you more examples, but you can find many examples in literature which talks about this application of fluorescence upconversion technique in studying this ultra fast processes like this charge transfer, twisted intramolecular charge transfer process, and how much time does it require for the charge transfer to take place fully. So these are the things that we can follow, and maybe more examples we will be able to provide you in the next classes in next lectures, some of the next lectures in different contexts involving proteins and other systems. So till then, have good time. Thank you.